Okay, so we're on number numbers. Oh, page 6, number 4. This is a particle motion problem. And hey, Maddie, can you hear me? Okay. Particle motion problem, but we're going to need a calculator to figure out what the graph looks like. Okay. So there's a velocity function. So we're going to type this into the calculator. So you'll go to y equals. Yep, type it in. But you're going to use the variable x. That's the only thing. And then you go to mode to double check that you're in radian mode. Okay, and then go to y equals, and you're going to type in, this is the velocity function. So think of this as the quote unquote derivative graph. Okay. Okay, so 4 sine x squared minus 2x plus 2. Now, this graph is kind of all over the place, so we really want to narrow our focus of this graph. So it says set the windows to x values -1, 5, and 6, 6. So that will allow us to adjust how far, how wide and how narrow to make our graph. So you're going to go to Windows. Do you see that Windows button here? Yes. Okay, so type in that Windows, and don't worry about the x scale or the y scale. You're just focusing on x min, x max. So x min, x max means what's the furthest left and furthest right on the x-axis that you want to show, and y min, y max is, you know, what's the lowest and highest y value we want the calculator to show. So it says from -1 to 5. And for y values from -6 to 6. And then when you're done, you'll hit that graph button. Graph. Up here. Oh. Okay. So this is what your graph should look like. Okay. So imagine this is the velocity graph. Okay. So, I mean, well, this is the velocity graph. This is the velocity graph. Then it says find the time when the object is motionless. So motionless means velocity is equal to what? 0. So that means anything on the x-axis. So we basically need the calculator, and it says from 0 to 4. So 0 to 4 is going to be 1, 2, 3, 4. So just to this point here, everything here, it doesn't need it, is not needed. But sometimes I like to look beyond my boundaries so I can just see what's around it. So how many places do you see the how many locations is velocity 0? 4. Okay. 3. Yeah. 1, 2, 3, 4. Okay.
Wait, what about the child? Oh, 0.
Actually, you know what? Just 3. 1, 2, 3. Because this is past 4. Okay. And oh yeah, we don't count this one because we only care from 0 to 4. Okay. So we want to look for those places. Okay. Now, this method is not as accurate. If you just hit trace, it kind of gets you there, but it's not as accurate as it could be. You see that? So we have a better way of finding the x-intercept. However, I mean, it's okay, but on the AP exam, they would need you to be more accurate. Okay, so this is the way that we're going to be more accurate in finding these three places where velocity is 0. So there is directions on page 19, which I'll just go over and talk through. Maybe this should say. Yeah. So the instructions here say. Second, I thought I had a larger copy to show.
You need this one.
No, I have. Okay. But it's just larger print. Would be nicer, but I don't have that. So to find these x-intercepts, we're going to go to second trace. Okay. So if we do second trace, you're going to be looking for an x-intercept. So click on that 0. Okay. So if you click on that 0, now you're going to place the cursor to the left of your target. So you see how right now my cursor is to the left of my target. This would be to the right over here, and this is to the left. Doesn't matter where you choose, just pick a point that is obviously off the x-intercept to the left of it. Right? Hit enter. And then you see that question mark here, right bound. So now you're going to scroll over to the other side of your x-axis. Hit enter again. And then you're going to see the word guess. You see that on your calculator, guess. So now the calculator knows your endpoints. So now it's going to be looking for that x-intercept for you. So you hit enter again, and it's going to zero in on that x-intercept, 2.463. You see that? Now, over here to the right, you see 4e to the negative 13. That's just basically a really, really, really small number. That's basically 0. So that's one of your x-intercept. Okay. So so that's one of our x-intercepts. So we can say t is equal to 2.463. Now we can go to try to find the other x-intercept. Yeah, do the same thing. Do second trace.
I did some of this last.
Okay, good.
2.454.
454. Okay. I'll show you in a second here. So you're looking for that point.
Yeah.
So second trace, 0.
Okay.
So I want to pick a point to the left of my x-intercept. So make sure you're off of your x-axis.
Okay.
Hit enter. And then you're gonna scroll to the other side of your x-axis. Hit enter again. And now the calculator is going to look for your target for you.
Okay.
Like yesterday, I don't know what I did. I didn't scroll to the right, but then it gave me back.
Okay, let's try again. Let's see.
No, I did it right like that. I was just wondering, I think I pressed the right button and then I moved back, so.
Yeah, hit trace again.
Oh, I was just wondering if,
Uh-huh.
where it said, I think it's 2.5 and like, is that correct? Was that?
I think the second one should be 3.299.
No. I was saying like, when I did this, I forgot how I did it, but it was like, I was trying to go back and do the other ones. And when I pressed the right thing, it gave me like when y was exactly 0. and it said x equals 2.5, it's like right on. the
Oh.
x-intercept. Yeah, no,
Yeah, for some, yeah. I guess if it says y equals 0, then that's fine, but
Okay.
mine was showing like.
oh, yeah,
like
yeah,
E.
because I did it right like that, and then when I was in that, and
Yeah.
I pressed the right arrow.
That I don't know,
I was
I don't
like,
know
oh.
why it would show 0.
If it doesn't get on.
Okay, okay,
So
so see if you can find the other.
X-intercepts.
you just go back.
Yeah, go back to second trace. So now you'll pick a point to the left of the second x-intercept. Left bound, scroll over to the right of it and enter. And you should be able to get that 3.298.
I says first curve.
Okay, let's see.
So try again, second trace. Remember, you're not doing intercept, you're doing 0. Yeah, you're looking for the x-intercept.
Yes.
So there we go.
Thank you.
3.409.
You did? Okay.
All right, let's see, try it again. Oh, it says guess, so let me see, hit enter one more time.
Okay.
There we go, yeah.
Okay, 3.298. Repeat the process again. And you'll get 3.903.
There it is, Mr. Rain. I did it.
Good.
No, the thing I want to show you.
Oh.
I just literally just pressed the right. This.
31.
From the second one, I literally just pressed the right. That's what it's.
Yes, but this may not be on the graph. It may be slightly off the graph. I mean, it is an x-intercept, but it's not on the graph. So we want to stay on the graph.
I just thought that was.
Okay, so we found these x-intercepts, right? So let me label them here. We found one of them to be 2.463. We found another one to be 3.298. No, I just wanted to give a visual. I mean, you have your calculator, but I want to be able to make markings on it. Okay, and then the last one is 3.903. Okay, so this is the derivative graph or velocity graph, okay? And we want to, it's asking when does the object change direction? So we have our t-values, but I like to create a velocity sign line so that we can get information that we need to get. So I'm going to create a velocity sign line here from 0 to 4. And I'm going to go ahead and place the t-values that I found. And if you think about what your velocity graph can do for you, you know that anything above the x-axis means velocity is what? Or positive velocity, yeah, so moving to the which direction, right, yeah. Anything below the x-axis means wherever the particle is moving to the left. Anything on the x-axis is where it's remaining motionless, right? So what's happening though between 0 and 2.463? Moving to moving to the right. Or you can just put plus if you want. Anything below is going to be moving left. Okay. So moving right, And then between 2.463 and 3.298, left because it's below. 3.298 to 3.903, plus above. And 3.903 to 4, it's, yep, that's right. We don't care about this part of the graph because we're only going to 4. So we're only going from 0 to 4. Yeah, but yeah, it's going to be that little portion that sits below. So this negative. Okay. So now it says, when does the object change direction? Well, we have the times when it's motionless. We have the sign line. Everything that we need is going to be on this graph. So these are also places where it changes direction, because not only does the object stop, it actually goes from right to left, left to right, right to left. So the same answer as part A, but we're able to produce more information. So object changes directions at these 3 t-values because velocity changes signs. And if I were to ask you, when is the object moving left or moving right, you can just pull that directly from your velocity sign line, right? You'll say, oh, moving right will be from 0 to 2.463, 3.299, 3.908. So having that velocity sign line is going to, be able to help you solve a lot of different questions if I were to ask you. Okay, so now part C, find the velocity of the object at t equals 3 seconds. Well, we can just plug 3 directly into the velocity function. You have your velocity function sitting there, so you can type in 3 one by one into the variable, or you can call the function and just make the calculator plug in for you. So the student told me a little bit of a shortcut. I didn't realize that if you do alpha trace, you can pick out the y value that you plugged it in. So y1 is holding your function right now. So you see how y1 is highlighted right now? Alpha trace. So if you hit y1, now I'm calling that function. And if I put parentheses 3, it's going to plug 3 into the velocity function for me and give me the value.
Oh.
So that's really nice. Trace, select y1, parentheses 3.
That's so funny.
Take it, enter. Parentheses 3. So it'll save you some time rather than, because before I thought you had to go to bars, y bars, all that, but there's a bit of a shortcut. We can get quickly to those values. Okay, so we have our velocity value. V of 3 equals. So what does that mean? What does that negative 3.836 mean? Not decreasing. Also, use a different word.
Moving left.
Moving left. Yeah, moving left. Moving left at this moment in time, right? At a speed or a velocity of meters per second. So now part D says find the acceleration. Well, acceleration is the what of velocity? Derivative. Yep. So we have a derivative feature for us here. So if we do math 8. Math 8 takes you to your n deriv feature. So d over dx. Again, because we already have the function assigned, you can just do second trace again or alpha trace again, pull that y1, and then plug in 3. Yeah. So now it's going to get to the acceleration function. It's going to plug in the t value for you. It's going to do a lot of stuff for you. You just have to be able to know how to get to it. So my acceleration is 4.539. And what's my unit of measure? Well, yeah, meters per second squared, yeah. Yeah, but yeah, I can say meters per second, or it can reduce, or you can clean it up and say meters per second squared. Okay, is the object speed increasing or decreasing? Well, increasing, decreasing speed, we have to compare the what? Signs of the velocity acceleration. So if they're the same, speed is increasing, but if they're different, speed is decreasing. Yeah. Speed is decreasing because v of 3 and a of 3, v of 3 is less than 0 and a of 3 is greater than 0, opposite signs. Okay, next one says find total displacement. Displacement is just the definite integral. Okay. So we just set it up, definite integral. So here's the formula for displacement. It's the definite integral from a to b of v of t dt. So we just plug this in the calculator and we'll go from 0 to 4. So you'll go from 0 to 4. So do math 9. Math 9 will get you to your definite integral notation, 0 to 4. And again, take advantage of the fact that you have the function already stored in y1 and go to alpha trace. Yeah, that saves so much time. Glad the student showed that to me.
They showed you like this.
Yeah, so I just found out. Saves like 3 or 4 keystrokes. So that means we know that in between 0 and 4, this object may be going back and forth, but in the end, it's going to end up 7 units further to the right than where it started. Okay, that's what that 7.75 means. Okay. And displacements, you see how velocity is meters per second, but then if you push it through the antiderivative, the rate is going to be stripped away and it's going to just be meters. Yeah. Now, total distance is a little bit different. Distance is, if the object is going back and forth, imagine you're walking forwards and backwards. You're counting each of your steps. So everything is going to be positive. So total distance, you got to involve what? Absolute value. So you write out that notation, definite integral from 0 to 4, absolute value of v of t. And then you can go to, again, same keystrokes here, math 9 from 0 to 4. Now we got to go to the absolute value feature. So you go to math number, you'll see that ABS as your first option. Yeah, we're going to go through the same problem in class, so you guys can help students around you. You're going to go to math, scroll over to number, math num. And then you're going to stick that y1 inside your absolute value bar. So alpha trace y1. So absolute value takes a little bit longer. For some reason, it just takes time to process. So it should be a larger value, especially if you're going back and forth. If your distance is the same as your displacement, that means this object never changes direction. It's just going to go either it's always moving to the right or always moving to the left. Okay, 12.177. Still meters though. Let's go ahead and skip H. I'm not going to ask you that question. H and I. So part J says, given my position at 0 seconds is 2, find x sub 4. So this is asking for final position. So this question has all three features in it. It's asking for displacement is how far are you from where you started? Total distance is how much did you move in total? And final position means if I tell you where this object started, how far is it, or where is it going to land on the x-axis? So the formula is final position equals initial plus displacement. So I'm going to write that formula here. So I'm looking for x sub 4. So x sub 4 is my final location. My initial is x sub 0. And I want to know how much progress did I make between these two times. So I'm starting on the x-axis on 2. And then from 0 to 4, I found that earlier, right? 7.753. So where is this object going to end up? It's going to end up at 9.753 on the x-axis. Maddie, maybe tomorrow I can answer that question for you. Because you're not here, it's hard to answer that. That's okay. Also, yeah, the calculator is going to be more accurate. Okay, part K, find the average velocity. So we have a formula for that. This is that's average value theorem. So we can reuse a lot of information here. So 1 over b minus a, integral from a to b of v of t. So my a and b values are 0 and 4. So 1 over 4 minus 0, from 0 to 4 of v of t dt. Now we already have this part, right? We already solved that. So we can just replace that with 7.753 divided by 4, and that's our average velocity. So we basically take how much total distance I traveled divided by 4, and that's, then I can find my average velocity. And don't worry about I, don't worry about L. Yeah. We'll get to that a little bit later. Future units. I don't want to do too much at once. Oh, and then average velocity is meters per second, right? So that's why I have to include that meters per second. Yes.
Is it origin? Yeah. Feature reserved to launch.
I'm not sure. We'll just kind of
Go.
yeah, kind of go where we can.
Sharing the elevation.
Mhm.
A bit.
Yeah, that's wrong.